In this lesson, we're going to turn our study of gases to a much more practical concern, which is how do I collect a gas in lab if I want to do a reaction? And by practical, I mean this is our next lab. This is what we're going to be doing. So there's a really common technique for collecting a gas that's made in lab. You can collect that gas over water. And it's really common because it's really easy to determine the volume of the gas that you collect. And with a little bit of sort of clever thinking, it's pretty easy to figure out the pressure and temperature as well. Now, so it's an easy technique, but of course it comes with one particular problem that we're going to explore today, which is when you collect a gas over water, you need to make an adjustment. And today we're going to figure out what that adjustment is. Now, to get a sort of visual in your head, I love this little simulation because it will show pretty much what we're going to do in lab and pretty much how most of these lab setups go. So what I want you to do here is they're going to take a little bit of potassium chlorate, solid potassium chlorate, and they're going to heat it and do a decomposition. Now, earlier in the unit, you studied the decompositions of chlorates, hydroxides, and carbonates. And here, I want you to predict the products of this reaction and balance that reaction, and of course, write it in net ionic form. All right, let's see if you got it right. So potassium chlorate, when you take a little bit of heat to it with a Bunsen burner, will make potassium chloride and gas as an oxygen. And you can see the balancing. The net ionic's easy because there's no aqueous stuff, no soluble ions. Now when you heat it, of course, that oxygen gas is what we want. It's the gas product that we want to collect. And one of the common techniques is to take a graduated cylinder or a eudiometer tube, which we're going to learn about, fill it with water, and then as the gas gets collected, it will displace that water and you can see exactly what volume of gas you collected. I really like this simulation. One, because it shows you how easy it is to see the volume of gas that you collected, but I'm impressed by how much work they put into it. Watch this. If we go back, look at the water level in the bath. If water is coming out of the tube, the bath is going to fill up a little bit. So the fact that they took the time to do that is pretty cool. All right, so if we're looking at this and we're thinking we're going to do some stoichiometry with it, well, a common thing to do in lab is to calculate the percent yield of the gas that you made. Well, the theoretical yield is easy, right? If I had kept track of how much potassium chlorate I had in the beginning, I could do a little stoichiometry and figure out how many moles of oxygen I would be expecting at the end. The actual yield, well, we're sitting here looking at this actual gas in this graduated cylinder, and it's pretty easy to record the volume of that gas. And you know where we're headed with this, is if you can record the volume of this gas, the ideal gas law might be a great way to figure out how many moles of gas were actually made in lab, and then from there, percent yield is easy to calculate. All right. Now temperature can be a little tricky. But we're going to assume maybe the temperature in the lab will work pretty well because this gas is sitting in the lab. It's not being heated or anything. Sometimes you may say, well, if my water was really cold and I was bubbling up the oxygen through the water, maybe it got cold. Maybe you'd prefer to go with the temperature of your water. You might need to make some active decision making on lab day as to what this gas is closest to in temperature. All right, so with that introduction, let's look at how we can do one of these problems. So let's say we had 0.08 grams of potassium chlorate in that test tube in the beginning, and we heated it strongly. Clearly, that's what we need to calculate the theoretical yield. But the actual yield we're going to get from the actual amount of gas we made, the temperature that was in there that day, and the pressure. You can see that this is leading to sort of an ideal gas solution to figure out how many moles of oxygen were actually made. All right, now before I send you to this problem to do this problem and calculate the percent yield, I'm a little worried that at this moment you might be slapping your forehead on the desk and saying, Jones, come on, we just spent so much time doing gas stoichiometry. You're killing me with this. So I will make a deal with you. I will calculate the theoretical yield. I'll take the 0.08 grams and I'll convert it to moles of oxygen so that we can get the theoretical yield. But your job is to take the volume, the pressure, and the temperature and calculate the actual yield. All right, go to it and I'll do my part. All right, let me show you my part. So my part, let me gotta move myself over here for a second. My part, I started with my grams, I converted it to moles because you know I always show my gram to mole work. Now I'm going to do a before and after table, but obviously you could do it any way you wanted to. So I take my moles of potassium chlorate. It's the only reagent, so it has to be the limiting reagent. So it completely gets consumed. And in my oxygen goes up by 3x, starting from 0 because it's a product. And I make 9.84 times 10 to the minus 4th moles. So that is the theoretical yield. Notice I didn't do anything in lab. I could have calculated this before we even went into lab. So it's only how much you should make in theory. Now you all know, because you already did the calculation, did we really make this amount? I don't think we did we? And it's pretty uncommon in lab to actually get 100%. So let's find out what you guys did. Well, if you took the ideal gas law and you solved for moles, you got PV over RT, and you plugged in the 1 ATM, you plugged, oh, did you remember to change the units to liters? There's my R and there's my temperature. I forgot to draw a line though. In any case, this is how many moles we should actually get. So yeah, we did not get 100% yield. It was significantly less. Well, if we actually calculate the percent yield, easy enough, right? Actual divided by theoretical, plug in my numbers, and sure enough, I get 62.3%. To pat ourselves on the back. Good job. The only problem is, that's not right. Now, I don't think we made a mistake. I think we did our theoretical yield right. I think we did our actual yield right. But that's not the answer. The answer is actually 60.4% yield. So clearly there is something that we did not adjust for when we were doing this problem. And it was that we didn't do anything about the fact that this gas was collected over water. If you ever see a stoichiometry problem from here on out, you've got to look for this. Now remember, we just finished a WebAssign where you did a whole bunch of stoichiometry. I had to choose very carefully to find problems that they were not collecting it over water, because every single time we would have gotten the wrong answer because we would not have made the adjustment we're going to learn to make today. So watch out for this. This should raise alarm bells. If you ever see gases collected over water, you got to slow down and say, whoa, I noticed something. I'm going to have to make an adjustment. So what is that adjustment? What do we have to do? Well, let's go back to our simulation. They've already filled the graduated cylinder with oxygen. And the problem was that when we said that the pressure in here was 1 atm, because it was the same as the pressure outside, it turns out that that was not the only gas in there. It wasn't just oxygen. If you zoom in really closely, you're going to see that there are lots of things floating around here. There's oxygen and water, and what we were recording was the total pressure, which was made up of the pressure of those two things. So we really shouldn't have been using 1 atm. That was the total pressure. It turns out that a lot of the pressure, a large mole fraction, new word we learned, right? A large mole fraction of this container was oxygen. I think a majority of it, maybe 0.8 atm out of that 1 atm, maybe more, maybe less, was the oxygen, but a little bit of it was the water. And that's the adjustment we need to make whenever we collect a gas over water, because there's a little bit of humidity in that gas. And so we're going to have to subtract out that little bit of vapor pressure. All right, let's go look. So here was where the error we made was. We shouldn't have used 1 atm because that was not the dry pressure of oxygen. It was the total pressure, and we need to subtract out the water vapor pressure, and then we're going to run back through the math and see if we get the correct answer. So how do I subtract out the water vapor pressure? Well, if 1 atm was the total pressure, and I know that, if I know the vapor pressure of water, it's pretty easy to subtract out, and that's something that you always look up in a table. So let's look at this vapor pressure table. And I will tell you, in our remote learning environment, we're not going to be able to do one thing, which I always do with vapor pressure tables. I'll explain it in a minute to you. But let's look at this. So if, and let me make sure I have a good pen color. We need a good pen color. Let's go with green. So the vapor pressure of water is just the partial pressure of water, right? We learned that term partial pressure means just the pressure of one individual gas. So it's telling you what the pressure of water is, and we're going to look it up. It depends on the temperature that day. Now, before we get to the temperature that we use that day, I want to explain what's going on here. Imagine that we have a pot of, you're about to make some noodles, right? That's a handle. I gotta tell you, I'm a little surprised by the quality of my pot here. And if I put a lid on this pot, has a little handle right there, and I imagine that I'm pressing down on that pot with my hand. Of course, when the temperature's really cold, when it's just a bit above freezing, there's not going to be a lot of gaseous water up here. It's going to be pretty thin. You're going to have no problem holding that on. And as it warms up, we get into here right about 20 to 25 degrees, somewhere in there, we're starting to get to room temperature. And if you think about it, if you grab a bottle of water, I don't have much water left in here, room temperature, there's not a lot of pressure on there. It wouldn't be hard for me to hold that top on because there's not a lot of gas particles of water above it. There's a bit more than there was when it was really cold. And as you get warmer and warmer and warmer, imagine this is a hot summer day, 100 and something degrees. Well, if you leave water out on the street, it starts to evaporate really quickly because the vapor pressure of water is much higher. Now, as the pressure goes up, do you know what temperature water boils? Well, it boils at 100 degrees Celsius. If you said 212, you were thinking Fahrenheit. And look at what the vapor pressure of water is at 100 degrees Celsius. It's 760. That's no coincidence. That's atmospheric pressure. And what that means is the gas has gotten so gaseous above this that you would have a hard time holding that lid on, because not only does the gas have so much energy that it's starting to turn completely into gas, but it has so much energy to push your hand back and the atmosphere back, and that's why water starts to completely evaporate, right? That's why we call it boiling. Pretty darn cool, right? Now, one last cool thing, you guys know that the atmospheric pressure in Colorado is not 760. The atmospheric pressure in water is more like in here. It's actually probably somewhere a little bit lower than that, between these two. Water in Colorado typically boils at about 94 degrees, in the Denver area anyway. And that's because the vapor pressure of water is lower there, or the atmospheric pressure in Colorado is lower, so the water can start escaping at a much lower temperature. And if you were to go up to the top of Mount Everest, where the pressure is so low, the atmospheric pressure, you will see that water boils pretty darn low on mountaintops. So if you've ever been hiking, you'll see that happen. Now, that's a huge aside, but the point is, that's what vapor pressure is. Now, what temperature do we need? Well, we did it in an everyday ordinary lab at about 25 degrees Celsius. I think they said 298. So we need the vapor pressure of water at 25 degrees Celsius. That's the vapor pressure we are going to have to subtract away from 1 ATM. Now, of course, this table's in millimeters of mercury. And it's surprisingly hard to find a vapor pressure table that's in ATM. So we have to do a little unit conversion. Forgive my lack of showing work. But it turns out that this 23.8 millimeters of mercury is 0.0313 ATM. So that's what we have to subtract out from the total pressure. So let's do that. My total pressure was 1 ATM in lab. My vapor pressure was 0.0313. When I subtract it, the dry pressure, the partial pressure of oxygen, is 0.969. Now, I don't know about you. It depends on how type A you are. But you'll see that that's not a very big adjustment. The amount of pressure in the gas above the water in that graduated cylinder was mostly oxygen. If we hadn't made any adjustment at all, look how small that difference is. It's tiny. And it usually is tiny, but we still need to subtract it out. So if you ever get a large value for the amount of water you're subtracting out, if this is ever huge, you know something's wrong. It's going to be very, very small. It's not very humid in the gas above the liquid. It's pretty darn low vapor pressure. Now, of course, if we do the reaction at higher temperatures, we'll be subtracting out a much bigger amount. I mean, not 92.5, because we'd have to convert that to ATM, right? But it is a much larger amount. So the higher the temperature, the bigger this sort of error that we'd get if we didn't subtract out from water would be. So let's go back to our math and make our adjustment. So now we know the dry pressure of the oxygen, the pure oxygen pressure, the partial pressure of oxygen was 0.969 right there. We used to have 1 ATM, and now we've adjusted it by subtracting out the vapor pressure of water. If I run through the math exactly the same, because the volume's not going to change, the temperature's not going to change, I get a slight adjustment to my moles. If I plug that in, sure enough, I get my correct percent yield, and voila, we're done. Now this problem was a percent yield problem. But it's not just percent yield problems that we need to look for this. Anytime you collect a gas over water, you need to subtract out the vapor pressure of water. So this is the phrase that you are looking out for. And when you see that, you got to go, whoa, I need to pay attention to that because it shows up all the time. It's a major understanding. Okay. One last problem I want you to do. Actually, I think we're going to do 2 problems, but let's do a simple one first. I'll let you read this one, and I want you to figure out what is the dry pressure of that hydrogen. All right, did you get 750.5 torr? I didn't specify units, so if you have the same answer in 1 ATM, you are correct. That's exactly right. If this is the pressure that was collected, that's the total pressure. We are going to need to subtract out the vapor pressure of water, and hopefully you noticed it was at 20 degrees Celsius. Boom, 17.5 is the amount that we needed to subtract. Great job. Let's do one more. I'll let you read it, do your calculations, and put your answer in. Okay, let's see if you got the right answer. The answer was 0.07697. That seems like a lot of sig figs. Let me check. Oh yeah, there were a lot of sig figs in this one. But it was not 0.08014. If you got that, what did you forget to subtract out? The vapor pressure of water. Or if you got something else, let's look at what other potential problems there are. That's not right. What other potential problems you could have gotten? One is make sure you went to grams. They asked for grams, right? You needed to convert this to ATM. Or did you? Yes, you did. You needed to, oh, that was an ATM. Did you remember to convert that to ATM? You don't need to convert this because this is just saying, look, this is the vapor pressure of water at that temperature. This is sort of the table it was looked up for you. But this, for sure, did you get that in Kelvin? You got 298 and you got 0.030 liters here. And if you're solving this, they say the reaction produces that much gas. You have your volume, your pressure, and your temperature. You can pivnert that to figure out the moles of oxygen that were made. And once you know that, then all you have to do is do a before and after table or any stoichiometry and work your way back from oxygen to figure out how much potassium chlorate was made. All right, great job.